Good morning, students. Welcome you all to this online lecture series on VLSI design. As you know, in the last few lectures, we revised in detail various basic details of VHDL. And in previous lecture, we studied in detail three components, that is data objects, classes, data types and operators. So in today's lecture, we are again going to do the revision of other VHDL basic components. As you see on the slide, today we are going to revise various details of overloading, logical operators, types of delays, entity and architecture declarations. So let's start our discussion with the very first topic of today's discussion, that is overloading. So what is overloading? The definition says that it is a process of having two or more functions with the same name but with different parameters. So what is the meaning of this statement? This says that in the VHDL, the operator is called overloaded if there is more than one function which is specified for different data and result types. So here it must be keep in mind that in the overloading case, the both functions can exist together. So main benefit of overloading is that it offers greater programming flexibility to the user. As you see, the overloading syntax is given on the right. The function with common name operator is declared which returns the value type. As you see, the same operator is declared again in the second statement, which may be used for different operation inside the same code. So let's take one example to understand this concept thoroughly. As you see in the example, when the operands are of type integer, then the built-in operator function is then called. And if the operands are of the type bit vector, then the function from package math is then called. And after that, the code is executed in the architecture section. So I hope you have now thorough understanding of this topic of overloading. So let's move to the next slide for the study of logical operators. The definition says that the operators are those which are used to perform specific operations inside the VHDL code. As you know, there are many predefined operators in the VHDL language, like logical operators, relational operators, adding operators, multiplying operators and miscellaneous operators. Now the logical operators are basically of 6 types, that is logical AND, OR, NAND, NOR, XOR and logical NOT. So let's take examples to understand these logical operators. As you see, the logical AND can be applied as Z is assigned the value A and B. Similarly, for logical NAND, the Z is assigned the value A NAND B. And in the next statement, for the logical NOR, the Z is assigned the value A NAND B. Similarly, for logical NOT, Z is assigned the value NOT A. And for the logical OR, Z is assigned value A or B. And for the XOR gate logic, the code is Z is assigned the value A XOR B. So in this way, the logical operators are applied in the VHDL codes. I hope you have now thorough understanding of this topic of logical operators. Now let's move to the next slide for the study of type of delays. So what is the meaning of delay? These are the statements which are used in the VHDL code to control the propagation times. What that means is, it means the delay mechanism provides control of the propagation time of the given system. But here one thing must be kept in mind, that delays are always specified in signal assignment statements. Now what is the use of delays in simulation? The delays are useful in simulation models to estimate delays in the synthesizable designs. So let's study various types of delays. There are two types of delays in VHDL, that is inertial delay and transport delay. Let's discuss these two in detail now. First of all, what is inertial delay? The inertial delay is that delay where the output appears due to the input signal after the specified delay. So in the VHDL, there is possibility to perform a signal assignment after a certain amount of specified time. Also, it must be noted that these are default delays, and also these are used to model the component delays. And also it is practically observed that inertial delay or inertial delay models are mostly found in switching circuits. As you see on the next slide, the propagation delay is that in which the transport delay models, the propagation delay is that in which the transport delay models the behavior of a wire in which all pulses are propagated. What that means is, this means this delay is not dependent upon the width of the pulse which is used, and this is widely used in interconnections. So also it must be noted that various routing delays can be modeled using transport delay. I hope you have now thorough understanding of this topic of type of delays. Now let's move to the next slide for the study of entity declaration. So what is entity declaration? The definition says that entity declaration specifies the external interface of an entity. This means an entity is the description of the interface between a design and its external environment. Another very important concept related to entity is that it has port declarations, using which the circuit codes are accessed from outside. So let's observe its syntax. As you see, in the entity declaration part, the entity name is specified. Under that, other components, whether general declarations, port declarations, constant, types and signals are declared along with their type, like bit vector, etc., and then entity is closed. So let's observe its example on the right to understand this concept thoroughly. As you see, the entity full adder is declared, under which various components are declared such as A, B and C in for input and of the type bit, and sum and C out is declared for output with the type bit, and then this entity is closed for the full adder. Now let's discuss architecture declarations. As you see on the slide, the architecture statement describes the underlying functionality of an entity. So we can say that an architecture statement defines the structure or description of a design which is bounded with an entity. See its syntax. The architecture with architecture name is specified as per the initial entity name declared before this. After this, all the logical equations are specified for the execution of the desired action. So all the statements are defined after this initial declaration of the architecture, and then architecture name is closed. Now there are three types of architecture declaration styles, that is behavior style, data flow style, and structural style. So let's discuss these three one by one. So first of all, what is behavioral style of architecture declaration? This style basically specified what task particular system is going to do in the written code, but it does not provide any details as to how a design is to be implemented. So it uses process unit for its behavioral description of the full ladder, as you see in this example. As you see, the architecture behavior style for full ladder is declared, under which process is declared for the variables which are declared in the entity part, such as A, B, and C in for input. The logical equations are defined for sum and C out for performing the logical execution of the code, and after that all the logical possible algorithm statements of full ladder are applied. The architecture is closed then for the full ladder. In this way, this behavioral style of architecture is declared inside the code. So now let's discuss another type, style declaration. As you see on the slide, the data flow style is that which specifies a system as a concurrent representation of flow of control and movement of data. And the other important feature of this style is that it models the information flow or data flow behavior of the combinational circuit. So that circuit may be of adder, comparator, decoder, or other logical circuits. Let's observe its one example. As you see in the example, the data flow architecture of the entity full adder is specified. Here the S signal is specified for the type bit, and then normal logical statements are specified for the execution of the desired logic. As you see, the S computes the logical AX or B, and then sum and C out is calculated after that. And after this, the architecture data flow is closed. So in this way, this data flow style of architecture is declared as per the VHDL code. So now let's discuss what is structural style of architecture declaration. Now the structural style is that which specifies the structural implementation of the code. So what that means is that it defines the structural implementation using component declarations and initialization. So let's discuss this concept with an example. Here the structural description of the full adder is shown, where this full adder is compiled by specifying two components, that is half adder and OR gate. As you see, various input and output parameters are declared in this component, such as L1 and L2 ports are declared for input with the type bit, and carry and sum are defined for output with the type bit, and then first component is closed. Similarly, in the second component, the port L1, L2 are specified for input, and O is declared for the output with both of type bit, and then signal is declared for N1, N2, N3 with the type bit to execute the desired logic using the above components. As you see, then the first half adder, that is HA1, is executed using above defined components and signal values. Similarly, the second half adder, that is HA2, is executed using above defined components and signal values. And then the OR gate logic is executed for OR 1 using above defined components and signal values. And then this architecture of structure is closed. So in this way, this type of architecture is practically used to execute the desired logic. I hope you have now thorough understanding of this topic of entity and architecture declaration. So this was all about today's lecture, where we studied in detail various basic details of VHDL. As you see on the next slide, in the next lecture, we shall start new topic, that is a review of MOS devices. So we shall revise and study in detail various topics such as MOS structures, enhancement and depletion transistor, and threshold voltage. Also, we shall discuss these topics with suitable examples in the next lecture. Thank you.